friends. Yeah, good evening friends. Welcome to Unacademy, which is the largest online education platform for GATE, CS and IT. Myself Mallesham Devasane. In this session, I'll be starting a new session which is about Turing machine. So what is the Turing machine and uh, what languages it can accept, that we are going to understand in this session. Before starting this session, let me introduce myself, because if you are new to this session, you should know about what I do, because of it might help you. Okay, I work as an educator on an academy in the segment GATE and ESE. Here I am going to take the classes for CS and IT branch. Okay, if in case you require a referral code, you can use DEVALIVE referral code to get 10% discount, as well as you can access all my free classes on Unacademy. So this is my profile link, unacademy.com/devagatesc. You can visit my profile and you can access all my free classes. Okay, if you want to know about me, you can read this slide. And also I have taken some courses which are very popular on Unacademy, C and TOC, as well as compiler. Yeah, so this is my referral code, DEVALIVE. Remember that, DEVALIVE. And in case if you are not aware of about Plus and Iconic subscriptions, these are the two subscriptions that we have on Unacademy. And Plus, we have many advantages, like you can attend any live class from any educator on Unacademy. That is the advantage. In each course, we will have weekly test and doubt solving session, and each course can be launched in two ways, that is English and Hindi separately. So you can attend any course, and these are the advantages of a Plus subscription. And Iconic, all the advantages of Plus. Additionally, you will be assigned with a coach, so that you will get a guidance and you can interact with educators, and also you will have a study plan and separate study material, and many other benefits are there. And in case if you wanted to know about my free classes, that you will get quizzes, all-in-one sessions, and TOC, C, CD, discrete maths, algorithm, special classes, and daily practice problem sessions, a number of sessions, and PYQ series for many subjects. And here if you go for classes, then you will find more than 400 classes on my profile. You can access them by visiting unacademy.com/devagatesc. And in case if you are not knowing about Unacademy Learning app, you can go to Play Store, Unacademy Learning app, you can search and you can install it, or you can visit URL using your mobile or your computer or PC, laptop or computer. Now choose here GATE and ESE. This is your goal if you are preparing GATE or ESE. And before that, just log in. You might require a code. You can use DEVALIVE as a referral code, and search for your classes, whatever you require, or you can click on subscription if you are interested for. So you can choose either Plus or Iconic. As I said, the benefits of Plus and benefits of Iconic. And now, what are the advantages you get? You will get a chance to learn from top educators of India. So you will have an access to every course from any educator on Unacademy if you take the Plus or Iconic subscription. And if you look at the plans, Plus, you have three very popular plans, 1.5 year, 2 years. Also you have other plans too if you are looking for 6 months and so on, but these are very benefit, you can get much benefit from this. And if you look at 1 year, 1.5 year, 2 years, you have a different price plans, but you should remember that you may enter DEVALIVE referral code to get discount. And Iconic subscription, you will have 1 year, 2 year plans. Similarly, you will have a different price for them, and you can use the referral code DEVALIVE. Now on this platform today, you have various classes on this channel, so you can access to all of them, right? Even 10 p.m. you have one more class, Memory Management by Khalil sir. Okay, and there are new initiatives from Unacademy where new batches announced by Unacademy batch wise. So each batch you will have the India's top educators, so you will get opportunity to learn from India's top educator in every batch. So the first batch is going to be launched from 21st December for electronics and electrical, and mechanical civil from 28th December, and CS and IT will be announced soon. And another initiative for all the branches like mechanical, civil, electrical, ESE, CS and IT, and chemical from December 20. And whoever studying in second year, third year, final year now, if you are in case preparing for 2022 and 23, even you are passed out student, and you get an opportunity to understand how to prepare for the 2022 and 2023 and complete roadmap to approach each subject of every branch and understand the subject wise strategy to crack GATE 2022 and 2023, and introduction and guidance by India's top educators across all branches. These are completely free series, so anybody from any branch that I have mentioned here, you can join this session and you can learn, you can know, or you will know that how to prepare for 2022 and 2023 for each subject, guys. So you will be having a special class for each subject, how to prepare for that subject in for GATE 2022 and 2023. Okay, so please share with your friends. That is going to be very good opportunity for you if you are preparing for 2022 and 2023. Fine. So I have some classes on Unacademy tomorrow 8 a.m. algorithms I will take. Even today I have taken, tomorrow also I am going to take 10 a.m. GATE PYQ series on C programming, and here the 10 a.m. just slightly shifted to 9:30 a.m. tomorrow because of 11 a.m. I have new batch. I am going to start a new course 11 a.m. the TOC, the part 1, the fast track course on TOC. So if you are already Plus a subscriber, or if you have not taken, you can take the subscription, you can attend these classes on Plus at 11 a.m. And then 2 p.m. we have CD GATE PYQ series on Unacademy, and 4 p.m. DBMS PYQ series on Unacademy, and 6 p.m. GATE PYQ series on discrete mathematics, okay, on Unacademy. These two are going to be topic wise from tomorrow, and 8:15 p.m. as usual we will meet here on this channel. Okay, you can share with your friends, or you can attend these free classes on Unacademy. Yeah, Simon, good evening. Shubhastri, good evening. Yeah, thank you joining today's session. And guys, please like the session. If you have not done it, please like the session. Yeah. So in this theory of computation, we have already completed the second topic, that is a push down automata, in which we have studied context free grammar and identifying CFLs, DCFLs, and closure properties, as well as we have seen normal forms. Many topics are covered in the previous sessions. Yes or no? In the last topic, in the last session especially, we have seen normal forms, Chomsky normal form and Grebec normal form. Also we have seen the CYK algorithm, and for the exam point of view, in semesters they may ask you CYK algorithm to show it, but in competitive exams they ask about CYK algorithm. What is the time complexity, and which parsing technique is a bottom-up parsing technique, and which programming, which designing which algorithm we are going to use, a dynamic programming algorithm, and so on. The many things they can be asked about algorithm rather than the actual algorithm. Fine. In this session we are looking at Turing machine. Thank you. Thank you so much. Turing machines. What are the things we are going to learn in the Turing machine? Like, let's look at. We are going to focus on definition of Turing machine. You know, in this chapter, if anything is important, that is a definition of TM only. I can tell you one thing. If you are getting any problem in this chapter, come to the Turing machine, learn what is the Turing machine first. I can guarantee that you will get at least some idea what we are going to do in the future. So the most important word, exactly, Shubhasri, that was right. And most important point in this chapter is definition and TM configuration. And you have designed only PDA and finite automata, and after finite automata, these things we don't have much practice, but still we talk about those machines because to understand the languages accepted by them. Remember that. Even we don't have much practice, we are not going to do much practice on Turing machine construction, but still we will talk a lot about Turing machine only. And then we will understand recursive languages versus recursively enumerable languages. Okay. This is today's agenda. In this session, I am going to talk about each and every one in detail. Let's start with a Turing machine. What is this Turing machine? You know, if I say finite automata, what is finite automata? You say it accepts a regular. And how it accepts a regular? If the string is valid, it holds at final. If the string is invalid, it holds at non-final. But actual definition depends on what type of machine you design. Is it deterministic or non-deterministic? Remember. The same way, the Turing machine definition I am writing here, guys. Theoretically it is. Okay. I am assuming this is some Turing machine. This is some Turing machine. This accepts some language. Let's say L. Accepts some language L. Sorry guys. And you will have some input here. Input that I am calling as a W. The most important point of this Turing machine is this input can be grammar, this input can be a language, this input can be a machine. That is what we are going to understand slowly, guys. But initially I can't help you that input is a language how we understand, right? So finite automata input is a string, but Turing machine input need not be a string. But that string that we have seen in finite automata and PDA, this string can be anything. So most of the people, they do not aware of what is this input because they still assume it is a string. It's a normal string that is a sequence of symbols. But basically this input is going to vary in the Turing machine, the first point. And anyhow, that I will talk about slowly. And if W belongs to L, W not belongs to L. In previous machines, finite automata PDA, the machine at any cost definitely holds, whether it is DTM or NTM, whether it is a DFA or NFA or DPD or NPDA, the machine definitely holds all the time. Here, this TM holds at final state. How it holds? If it is DTM, deterministic Turing machine, it will have exactly one path. If it is NTM, at least one path you have that holds at final. And if the string is invalid, we do not know. It depends on the machine. It depends. It means it might halt, may halt at non-final. You can ensure if it is, you can design, or it never halts. It's just like a program, you have infinite loop, right? Here there is some kind of nature you have on the Turing machine. It never halts. So you have two choices. It may never halt or it may halt at non-final. So one of the case will happen when the string is invalid. So most of the people, they should talk about, note, the Turing machine definition is about valid strings. I can guarantee every valid string of L, TM always halts. If the TM that accepts L, TM always halts in case TM is accepting L. Everybody, doesn't matter you talk about invalid string or not, because it's some problems you may design always halts at non-final, some problems you can design even never halts if you want it. Clear this point? And at any cost, this definition is important, because if you do not remember this definition, there is no word you can understand in this chapter. Everybody, a Turing machine's topic especially depends on the definition of just a Turing machine, because we are not going to implement the practical everything here. Okay, definition of TM, I will recap this after some time. Let's move on to configuration. How the configuration of TM, the standard Turing machine I am talking about. And do you think only one Turing machine in the world? No. You can build, like, if you are purchasing the computer, computers are many types today, and right, configurations of computers are many types, right? Single processor, quad processor, so many are there. Even Intel, Motorola processor, so many configurations. And here I am talking about standard Turing machine. Okay, you can write one-way tape or two-way tape. Both are standard, but I'm just using one way. That's fine. If you want to use two-way, just you have to say 3 dots here, 3 dots here, because both sides infinite. If you want it, the one way means just you can start from one side. So I'm keeping here arrow. So let me take two-way infinite tape. That's fine. And here this is the finite control. Any machine in the world, it must have the finite control. You cannot write the infinite configuration. And suppose let's say this tape can contain a machine, can contain sequence of symbols, can contain grammar. It's your choice. And just we are very good at understanding the string sequence of symbols. I'm keeping that. And this is almost looks like finite automata only. But what is the difference between finite automata and TM? This head is going to increase its power. Like you have additional thing like write also at the same time. Read, write, head. You can read on the tape, you read from the tape, or you can write onto the tape. And direction is both directions you can move. Now you have head is bidirectional, and on the tape you can read, or you can write, or you can read from the tape, right? So this is input or output tape. Input, you can say simply tape. Rather than saying input output, just say tape. This is a tape. You can write or you can read, right? If you want to represent only input, you can represent, no problem at all. And now look at what are the parameters we have. Now Turing machine is equal Q, that the finite control has finite number of states, sigma, and delta Q naught F is exactly like a finite automata. Additionally, what do you have? The special symbols which are called as a blank. And before after input you will have blank symbols by assumption. So blank is a special symbol on the tape. The whole tape occupied with the blank except your input initially. And another one is a tau. Tau represents your tape alphabet. This is a special symbol called as a blank. Yes, Anvesha, I am covering everything in the TM exactly. Yeah, Agarwal, Ram Ram. Right. Tau is the tape alphabet. Now additional other parameters you might know about it. In DFA, infinite automata, PDA, you have learned them. That this is set of states. And sigma is alphabet, input alphabet. Now only the difference now, what is input alphabet and output alphabet? That takes a little bit time to understand. Input alphabet, let's say sigma is equal to here A comma B. And what is tape alphabet? That is tau. Here A is there, B is there, that is also on the tape, and a blank is there. Additionally, after some time, you might replace with this A with X, or this B you might replace with Y. So might additionally come X comma Y if you want it. If you design the machine that way, I want to replace A with X in future, I want to replace B with Y in future, then X, Y are new symbols which are not there in the input. You have created on the tape specially. So all the input symbols are there on the tape. Additionally, you will have new symbols that you write onto the tape, and also the blank symbol which is by default we assume, right? And delta, that takes some time. That is a transition function. That depends on what type of Turing machine you design, deterministic or non-deterministic. Yeah, Q naught, initial state. And F is the set of final states. The same, all configurations are same, all parameters are same except that last two, right? Now delta, what is the delta is name is same, but it is defined differently now. It is defined differently now. Here we have two kinds of machines, DTM and NTM. Of course, DTM equivalent to NTM. You can convert one machine to other machine, remember that. But what is a deterministic Turing machine definition? Here, delta is Q cross tau. Sigma is there inside the subset of tau now. If you ask me the relation, the sigma is strictly subset. Of course, you can write equal if you want it, tau. Clear? Sigma is the subset of tau. So instead of writing sigma, tau is the best choice. And you will go to next state. You will write with some symbol. You will move either left or right. And some of the Turing machine, they can stay there. Right? It depends on the Turing machine configuration. The definition also can change. But this is the standard definition of the DTM. And don't assume this is the definition used for every Turing machine is wrong. There are different types of Turing machines are there, configurations are different, then the DTM definition slightly can change. And for the NTM, delta is Q cross tau derives 2 power Q cross tau cross L comma R. You will have non-deterministic choices for NTM. Yeah. And I will just request everybody, whoever have a confusion in recursive and RE languages, only the best solution is follow from the first lecture to the last lecture in a sequence without ignoring any topic, because I am going to cover everything. But if you are ignoring any topic any day, then definitely it will be connected to the next day and you can't get idea what we explain basically. Fine? Okay. Now this is important, but initially it looks like you can't understand any parameter directly, because you need to have a construction of Turing machine, then you will get an idea of each parameter. So right now you are not aware of anything. So I can't help you about this definition. When we construct, I can talk about this definition, how it works. Right now I'm just ignoring them. Let's go to theoretical points. What is my agenda? To cover theoretical points first. Before looking at actual TM, let's look at what are these different machines. And we have finite automata and we have push down automata, and we have LBA and HTM and TM. What are the differences we have here? Before learning about Turing machine, okay, how do you speak this terminology? Everybody knows, I hope everybody knows about the abbreviation. No confusion about the abbreviation, finite automata. And no memory in that finite, only states are going to remember everything. In push down automata, you have a stack to remember something, and linear bound automata. And HTM is halting Turing machine. And Turing machine, obviously you know it. That's the word I'm using. Okay, most of the people are not aware of the last three words. So I'm going to talk about here. In the finite automata, we do not have any extra memory. So it just, you will have a finite control, no memory at all. Right? Everybody knows that. But push-down automata, one stack extra apart from your control. You can just maintain one data structure. Here I can say no additional memory except the states. States can remember only finite memory, remember. So no additional memory. Here stack is the special memory you have it, extra memory. Linear bound automata, HTM, all three basically guys, remember all the three are Turing machines only. All the three are Turing machines. But they are going to be defined a different way. Remember, the last three are Turing machines. But how do you understand this is the tape length. The tape length is restricted here. Tape length is bounded, linearly bounded. You cannot use unbounded tape. Right? You can't assume you have infinite tape. Remember that. To solve a particular problem. But in HTM, here it is a Turing machine. TM that always halts. That it is a TM that always halts. Here you can say LBA, it is HTM. HTM you can say because it is also always halts. It is HTM but tape length is bounded. And what is HTM? It is a TM that always halts. Then what is a TM? What is a TM? It always halts for valid strings. It always guarantee halts for all valid strings. But when you are talking about HTM, doesn't matter valid or invalid, it is going to halt for both. TM that always halts, whether it is valid or invalid, we don't care. Both it will halt. Both valid and invalid members, it is going to halt. Everybody? That is HTM. And LBA, it is going to use the tape length is bounded linearly, but it is not going to use in exponential tape. You can say that. Okay, not much correct, but it is. And this is how we differentiate. When it is finite automata, you can understand only regular languages. When you have this stack, you can understand CFLs in which you can have all the regulars and some of all regulars you can understand, and also some non-regulars. Some means infinite only. And when it comes to LBA, you can understand all context-sensitive languages in which all context-free languages comes, additionally some non-CFLs. And HTM, it is going to understand recursive languages. Recursives. And Turing machine is about RE languages. Everybody, this is a very simple definition of all the machines, guys. It's going to be very interesting if you want to do the research on the Turing machine. But only as per the exam point of view, Turing machine we don't do much, but we want to learn the theory part. Okay. Now let's focus on before recursive, let me help you one thing. Here we have a finite automata mainly, and PDA and LBA and Turing machine. Anyhow, HTM is also a Turing machine, but a special criteria, it always solves. And in this finite automata, you have deterministic machine and non-deterministic machine, both are equivalent. In PDA, DPDA, if you design for all the DCFLs, that power, you can say that you have less power than a PDA, because PDA can be designed for more languages than DPDA languages. LBA, you have deterministic LBA and non-deterministic LBA, but there is no relation till today, and by default we assume NLBA because there is no algorithm to prove these two are equivalent today and no relation between them. And Turing machine, here we have algorithms to prove DTM is equivalent to NTM. Everybody? LBA definition is also exactly like TM, but LBA always halts, but it should use a bounded tape only. Everybody? Yeah. If you are watching this video, guys, please like this session. Please like this session, guys. Thank you so much. Okay, now let me talk about the recursive language. Now I have told you the recursive language is accepted by halting Turing machine. So before recursive, you can understand more about recursively enumerable. We are going to use the abbreviation for this is REL, or simply you can say RE, right? This recursively enumerable language can be accepted or can be enumerated by Turing machine. There are two choices you have. So if you are designing Turing machine, TM can accept REL. Here TM can enumerate. It can produce even REL. You have two choices. Either you can accept or you can enumerate. Right? We have many names for this REL. I will just talk about after this. Okay, many names for the same language, guys. If it is accepting REL, then how do you understand that language or machine? You give some input. That input belongs to language. Let's say W belongs to L. This TM accepts some REL, you can say L is the language. Here the behavior is, if W belongs to L, definitely halts at final. Means it is accepted. The string is accepted. Every string belongs to L is going to halt at final. If the string is not belongs to L, it will guarantee it will not halt at final, but you do not know whether it halts at non-final or it goes to infinite loop, such things. Everybody, this is just a definition of Turing machine. The first slide I have shown you the same thing, guys. Look at how many times I repeat the same definition. And another one, if TM enumerates REL, input is not important here. What is important? What it produces. This Turing machine enumerates REL. So it is going to enumerate the strings W1, W2, W3 and so on. And here every W that you see here, WI, all WI that are belongs to L only. So invalid strings we don't generate here. And this machine is very special. It knows how to enumerate every valid string because it has the logic to produce the valid strings, guys. Clear this point? Come on. So Turing machine can accept REL, can enumerate REL. You can map with a real-time example, guys. Like best example that I can tell you, we are learning TOC together. I am delivering the TOC. So I am the enumerator. So I am the Turing machine. I am enumerating the theory of computation. Assume TOC is a language. Now, as you are the Turing machine, you are recognizing the words one by one. Yes or no? Which are not there in the TOC, you are not worried. Which are not there in the TOC, I am also not worried. We are both Turing machines. You are the acceptor, I am the enumerator. So this Turing machine is a student, is called as acceptor. It's just like a student. And this another Turing machine is enumerator. You can call it as enumerator. It's just like now you have educator, faculty. Here I am delivering the words which are there in the TOC and you are trying to understand the words which are there in TOC. Okay, this is how you can connect theory of computation with the two kinds of machines. Right? Example, the first Turing machine acceptance, I can check whether the given number is prime or not. The second Turing machine will produce only prime numbers one after other. So here prime language is understood by the both machines. One trying to understand given number is prime or not. Second, it is just producing the prime numbers only. But that is what we require to understand what is your language. Here your language is a prime language. Like prime language, theory of computation, you can map with anybody in the world. So everybody clear about recursively enumerable language? Here one thing is missing. I am not talking about invalid strings. Why? Because invalid strings may halt, may not halt. That depends on what kind of language you are looking at. If you are looking at regular language Obviously every regular is recursively enumerable. Then invalid string also you can frame a logic yourself. It is your choice, that's all. But when it comes to recursive language, I can say that there exists a Turing machine. I am not saying that every Turing machine in the world. There exists a Turing machine that always halts. There exists, remember, not every Turing machine, remember. There exists a TM that always halts. And also that accepts one language, it is called as recursive language. There exists a TM that always halts to accept a language. That language is called as recursive language, guys. Everybody, that means I can design some Turing machine like this. Look at theory. You should have the patience to learn. That is the reason the most of the people they avoid learning Turing machine. The only reason is without showing anything we speak a lot. Like the books, they write so much information but they don't explain to you. You need to understand. The same way I am speaking a lot without showing exactly what is it. Fine. Now this is also a TM. This is also what? TM. But that always halts. Whether it is valid or invalid, but what it accepts. Some L, that L is called as a recursive language, guys. Now give some string W here, input. And if W belongs to L, definitely halts. W not in L, definitely halts. Doesn't matter whether you give valid string or invalid string. It halts, but where it halts, that matters. It halts at final with exactly one path or at least one path is there. That depends on type of machine. You can use a DTM or STM. That doesn't matter. But you should show that it always halts. So all set final state. Here all set non-final state. Clear, guys? Halts at non-final state. Now both sides you can see that whether the given input is valid or invalid. If it is valid, it all set final. If it is invalid, all set non-final. Because we can always design some Turing machine that always halts. But every Turing machine that accepts recursive, will it halt always? No guarantee, guys. For recursive language, we can build a Turing machine. We can build halting Turing machine. Remember that point. Don't say every Turing machine that is always halts wrong. We should say there exists a TM that always halts. There exists, no doubt. Okay, this is about acceptor. Guys. We can build acceptor. Another one, we have a special machine. A Turing machine can enumerate. But this time we have a different strategy, guys. This Turing machine enumerates L, you can say effectively enumerates, or you can say TM enumerates L in lexicographical order. All the strings of L will enumerate in lexicographical order. It can be dictionary order, it can be particular order, but it has internally a lot of meaning, guys. And here I might be producing like W1, then W2. This is the dictionary or lexicographical order. And here also, but this order is well defined, guys. This is a lexicographical order, effective order. Internally there is a lot of meaning for normal enumeration and this lexicographical enumeration, guys. If any language is enumerable lexicographically, that language is called as recursive language. And what is recursively enumerable? Any language is enumerated by TM, that is RE. I don't say is it lexicographical order or not. I don't know. Right? We don't say that word. It can be, it may not be. Remember. So these are the two definitions of our recursive language. And here we have two definitions of RE language. Now what is important to know about these words? To know about these words, guys. Okay, before knowing about the words of the recursive and REL, let me tell you again one more time actually what are the benefits of their plus and iconic subscription. And do not forget, if you are interested to take the subscription, DEVALIVE is my referral code. You can see on every slide DEVALIVE is my referral code. Then why we keep it? Because you will get an advantage of 10% discount. If you don't apply the code, you may not avail this benefit. So that is the only reason DEVALIVE I keep every slide. But let's begin. You have structured courses. Means what do you mean by structured courses? Like it's a well planned. If I'm going to start the course from tomorrow, I'm starting the course, guys, December 17th to December 31st. Every day schedule will be given to you, like 11 a.m. to 1 p.m. I take TOC from tomorrow. I've started one course. Then you will be knowing exact schedule, what timings on which day, and every Sunday you will have a quiz, and every fourth day you will have a doubt session. It's well organized and will be launched, and you can see and you can plan well. And not only that, multiple courses for the same subject. TOC I am taking now, and you have many educators on Unacademy can teach TOC, but you will be always knowing by looking at the profile, by looking at by knowing the awareness of the educators, you can attend as per your knowledge and study as per your interest. That is important. Learn from India's top educators. You can learn from them and study with proper planning. Enjoy learning without losing the confidence, and you will get a beautiful journey throughout your preparation. So this is the best of my knowledge that you will get benefit from plus and iconic subscription, guys. Okay, now we have I told you one thing. We have many words, guys. Let me introduce some words now. Right? Let me introduce some words. One is recursive language. Another one is RE, means recursively enumerable language. There are many names for them. Synonyms, I am talking about synonyms. I'm just talking about synonyms. This can be called as many ways, with many other names. Recursive language also called as, another name is decidable language, guys. If you do not know about it, remember it, decidable language. What is another name? You can also call Turing decidable language, or TM decidable, you can say that. Apart from this, what are other names you can use? This language is a lexicographically enumerable. You can say effective enumerable language. By whom? By Turing machine only. Because by default we only talk about Turing machine in the world, right? And these are the very important words for the recursive language, right? For the recursive language. And RE language, we have simply a name called as enumerable language. You can simply call enumerable. And what are other names? You have acceptable. What are other names? A recognizable. If you want to use Turing machine like TM acceptable, TM enumerable, that you can use a word if you want. TM enumerable, that is optional. You don't need to use that word if you don't want. Simply I say Turing recognizable, then which language it is called as? Recursively enumerable. Another name of recursively enumerable you can call Turing recognizable. So these are the best words. Even there is another name, guys, I forgot to tell you, semi-decidable. That is very, very important one. Semi-decidable language. It's another name of RE language. Semi-decidable, partially decidable, you can say that. Everybody, so if you look at the relation, every decidable is a semi-decidable. Remember the relation. Let me talk about some important relations that you may require to know, like Chomsky character, right? Just I'm doing the same thing. I'm just doing the same thing. Okay, what do you know about this? These are regular languages. Not one, infinite regular languages are there in this box. In this box, infinite regular languages. And here, all context-free languages are there inside this box. Here, these are CFLs but not regular. And everybody, whether it is regular or outside regular languages class, they're all context-free languages only. And here, all CSL, context-sensitive languages. Anyhow, context-sensitive languages, we are less interested now. You can use that another name which is a superset of the other class. All recursive languages. Context-sensitive languages are inside. There is one more box is there. I didn't draw it. We are not interested at all now. Here all RE languages. Every RE languages including regular. Every regular is also recursive. Here so many points are there, guys. Yeah, exactly. The box name is set of regulars and dot name is the regular. You can say that. There are two words here. Now, right now I am not worried about that. So what is the relation I can form here? Can I say every regular set is, you can say CFL, you can say CFL is, I can say CSL, I can say is recursive, is REL. Every regular set I can use that word. And similarly you can have every CFL is dash. What can I answer? I can answer CSL, I can answer recursive, I can answer even REL. So like that, every language you can map with another language to understand. Yeah. But only one word that you might confuse. Yes. Set of all regulars is a one set in which every regular is there, is inside the set of, the subset of all CFLs. Don't say one CFL, remember. This is a different relation. One box is in another box. It's actually all CFLs are written. Actually you can write set of all CFLs. That is the best word. Only to understand I am writing that way. This is set of all regulars inside. Clear this point? Yeah. And here, if I ask, what are the machines I can design for regular languages? I can design one regular language, I can design one finite automata, and one regular language I can design push-down automata, or I can design linear bound automata, I can design alternate Turing machine, I can design Turing machine. You have many options for one language, guys. If the language is regular, I can show you finite automata, I can show you PDA, because every regular is also CFL. So every regular I have many choices. So do not confuse this one. We know every regular language we can design FA, we can design PDA, we can design LBA, we can design HTM, we can design TM. But how do you say that? Definitely finite automata exist. You can say that. Definitely finite automata exist. And it, in the sense, everybody else is also exist. Remember. So we have to say for every regular language, there is a finite automata that accepts. That doesn't mean that only finite automata. Remember, you can design powerful machines too. Right? This is the most important one. Now, today we will understand few important points, because tomorrow I am going to help you to construct the Turing machine. Before that, every definition, every word that we are going to use, you must keep here. So now we have a Turing machine, and you might know that I want to read a symbol. Like let me say something. Let me say something. I have A here. I have A here. I want to read A. Read, just read. Don't do anything. Just read it and move one direction to the right, because you can move any direction. Right? Let's say I am moving from Q0 to, let's say, Q1. And I am taking which direction? Right direction. but I am not writing with any other symbol. So what is happening? How to read a symbol? You can also move left. Your logic will demand which side you want to go. Okay, how do I represent this? Here, transition from Q0. By reading A, I am moving to Q1, but I am replacing with A and I will move right direction. So here, this Q0 belongs to Q. This you can assume present state just now, and this A is at the tape symbol, because in future it may not be input, guys. A might be capital X. Who knows that? Tape symbol, instead of input, you say better to say tape symbol. And Q1 is going to be next state. And other A, this tape symbol you are trying to read, and this you are trying to write with some other tape symbol. And that is how we represent, guys. The same tape symbol we see before and after transition, then that means you have read. You didn't write with anybody else. So R means it's a direction. Direction. You are moving right direction. You can also move left if you want to move. Clear? And how do you draw a diagram for that? From Q0, I will move to Q1, and here A is the first parameter that you read, and you can write so many ways. A comma A. That means I'm writing with A and I move right direction. Everybody? This is a direction. You can represent as a triplet. The same thing you can represent many other ways, guys. You can also represent many other ways. I can also write A comma right. Right, I can use right arrow. If it is left, right, left. You can also do that. Arrows also you can represent. Yeah. There are many representations. Even I can use A, represent A comma right. This is also fine. That means A was before transition, this A was after transition, and this is the direction. So read, write, and then direction. So understand, doesn't matter what representation I use, I must specify 3 parameters. First one is the read, second one is the write, third one is the direction. This is standard representation. Okay, this is how to read and how to write a symbol. Now we have a tape. We have A, I want to replace with, let's say, X, and I might move right direction. Some other symbol might be there. Okay, let's say Q to Q dash. So how do I refine? From state Q, by reading A, I will go to the Q prime and I will replace A with X and take right direction. Everybody, how to represent that? This is the present state. Assume that way, and you are reading A, one of the tape symbol, and Q dash is the next state, and X is that you are writing with, and R is the direction you are moving right direction. Clear? And now I can draw a diagram. If you are representing a diagram, you should be very patient, because this is just like a program, guys. Just like a program. And from Q you are moving to Q dash, and that A I replace with X and I move right. And always map properly. This is A here, this X is here, this R is here. Clear this point? You need to understand how do you represent. Even you can represent a table, guys. That Q, when you are reading A, you have Q dash and you replace with X and you take right direction. This is a delta table. Guys. Okay, this is a table representation and diagram representation and mathematical representation. You can also use the function mathematical representation. Fine. How to remember a symbol? Now, Shubhasri, now you don't recognize anything. You don't know any problem in the world. Right? First, we will understand a problem. Now you don't know anything about recognition. I am only asking, how do you read, how do you write? I am asking. Right? How do you read? How do you write? How do you understand the given problem? That is different. The problem will decide will you read or will you write. Now don't worry Shubhasri, we have not started any problem. Why are you worried about? First you don't know what is there in the program. How can you write a program? Can you do that? I am helping you. What are the tokens? What is the syntax of the program? You are asking, sir, how to write a logic of the program. Very difficult now. How to remember a symbol? Now here you can try to understand. Finite automata. In finite automata, how did you remember a symbol? We have changed a state. That is how we learned. Here we remembered A. How do you know that? We remembered. Right? We remembered A here. How do you know that? We changed a state. Change state in finite automata because we don't have a memory. Change state, it means you remember it. Change state means you remembered it. Is it clear? That is how we did in finite automata because there is no memory here. There is no memory to keep anywhere. Only you can do change a state. That means somehow you remembered it even though you don't have a memory. Everybody? Yeah. That's about a finite automata. PDA, you have two options. You have two options, three options in case. One, you can change a state. That's like a finite automata when you don't want to remember, right? When you don't want to remember, when you want to remember finite length, you can change the states. But I want to remember unknown arbitrary length, then you can push onto the stack. Then later on, you can compare by popping it. And third, you can do both if you want. You can change state and also you can push. Both you can do that if you want it. And many ways to remember something. I want to remember A. Just change the state or just push onto the stack. Or you can do both, change the state and push onto the stack. There are many ways to remember something. Remember a symbol in a PDA. Clear? But Turing motion, how do you do that? Here, one, you may change the state exactly like a finite automata if you don't want to write it with anybody. And second, you can write with a symbol if you want. Write with some symbol, some other symbol so that you know that you have remembered it. A I replace with X. That means I remembered it. When I come back, I know A was not there means somebody representing it means I remembered it. Write with some other symbol. Write with some other symbol so that you indirectly remembered it. Clear? So these are the two things that you can use in the Turing motion. Whenever I say remember something, either you can write with somebody or you can change the state, depends on your requirement. Right? Fine. Of course you can do simultaneously both. That is what I need. Okay. Now if I want to construct the Turing motion anyhow today, right? So far we have only understood. Guys, remember, please attend the next session to know about the Turing motion construction. Today I am only introducing the basics because basics are important to understand the construction. And now I will give you an approach. Suppose I want to understand what is this language. Here we don't have a stack, but what we have a tape only. We have a tape only. Triple A, triple B, and we have tomorrow I will design, not today. Only I am giving hint. It is purely theoretical point, guys. Practically your wish, how do you want to implement. Guys, initially we will point to A. So what we do to remember, to understand this problem, you don't have a stack, you can't push onto the stack. What we do is, we do the scans. Like, if I want to remember this, first time I scan, I will replace A with X, I will replace B with Y. So I will replace these two. Everybody? And somehow I will come back, I will do second scan. This time what I do, I will replace second A with X and second B with Y. And somehow I will come back, I will scan again. This time what I am going to do, the third A I replace with X and third B I replace with Y. And somehow when I am coming back, I don't find any A, so I know that somehow to accept. Everybody, this is how we understand, because our head can move bidirectional. Now I can remember the symbols by writing with some other symbols. Here, who is the sigma? Sigma is what initially you have written onto the tape, A comma B. What is tau? Tau is a blank already there. Small a, small b are input symbols. Now newly you have written x and y. Everybody, here blank belongs to tau and sigma is a subset, strictly subset, remember that, tau. Everybody, and this is how we are going to proceed for the next session, guys. And it's not gonna be easy, because you might be thinking that Turing machine you can design in 1 minute only by practicing. First time you are learning the Turing machine, you need to understand the logic rather than your Turing machine construction. Logic is very important. So what is the logic I am doing here? If I want to understand A power n, B power n, what is our logic? We do scans. Scan, input. How? You need to do not one scan. You might do at least n scans. N scans. N scans you might do in forward direction. In each scan, what do? Remember I am saying it. Remember means you need to write with some other symbol. Remember 1A and 1B. How do you remember? 1A, remember means replace 1A with some other symbol like X or ash or dollar, something like that. This replace B with, how do you remember? Some other symbol. Don't replace with X, replace with somebody else, Y, let's say. Okay, scan the input. N times you do the scan, and n plus 1th scan you don't find A. That means input is over. We'll do something on tomorrow. Second, now you will understand, okay, how to accept now. Because now my input is over, how to accept that we may do n plus 1 scan, n plus 1 scan, that we don't have A, so that somehow we will understand tomorrow, right? Not today, we'll understand tomorrow. So from here onwards we will continue tomorrow, guys. So today what we have understood, definition of Turing machine, that's all, and configuration of Turing machine still we are trying to understand, because here delta still it's not over, because DTM, NTM, which takes much time to understand, right? Some people even don't understand what is exactly delta 2, right? So remember that DTM and NTM are equivalent, and when we are talking about HTM and TM, the HTM we can design either deterministic, DHTM if you want, and NHTM, that doesn't matter. Even DTM you can design, NTM here. Remember, they are equivalent. Here the nature is very important. So do not compare this deterministic is somewhat is called as HTM is wrong. Remember that. The Turing machine is only sometimes acts like ordinary Turing machine, but that machine can be designed either deterministically or non-deterministically. Fine. So these are the theoretical points today. And next class we are going to construct a Turing machine. In the next session, the construction of TM. And we don't do for many problems, but we do for few problems to understand how we can design a Turing machine. But theoretical points are more important than the designing of Turing machine. Remember. Okay, in the next class I'm going to help you a lot, and if you are going to attend tomorrow my sessions, you can follow my classes. And tomorrow I'm going to start the new course, that is every day 11 a.m. The plus course is going to begin. The plus are iconic people can attend my special class on TOC. There you will understand, how beautifully the course is designed. Okay, thank you so much for attending today's session. And if you don't know about plus or iconic, you can interact with us anytime to know about it. And mainly we have live interactive classes and weekly test doubt solving for plus, and iconic will have assigned with coach additional to the plus, and you will have a separate study material too. And this is my referral code. In case if you are coming to Unacademy, you want to access our classes, then use DEVALIVE to get an access to our free classes, as well as you can get the subscription. And this is my link to follow me unacademy.com/@DevaGateCSE. You can also click on follow button to get notifications of my classes on Unacademy. Okay, this is our Telegram channel. You can subscribe to us to get daily notifications from us. Right, so we have so many YouTube channels from Unacademy. Top educators of India are teaching on these channels, and you can share with your friends. And please enjoy our classes, and don't forget to like the sessions at the end, which is very important. Please like the session before leaving the video, and also share if you like it, and subscribe, and thanks so much. And HTM and TM is not same power, it's a less than TM, and LBA is less than HTM, and PDA is less than LBA, and Turing finite automata is less than PDA. This is the expressive power. This is the expressive power. Okay, anyhow, I'll discuss in the next session too. Bye bye, see you guys.